Hello everyone, thank you for coming to my presentation. My name is Jung Park and I'm from Professor Jin's Park Lab at Jeonnam University in South Korea. Today I'm gonna talk about the focal point analysis of focal surface waves. Focus transducers have a curved geometry forming a circular arc with a specific radius, as shown in this figure. This configuration enables the source to converge at a focal point. So focus transducers can generate a narrow and strong beam, making them especially effective for manipulating microflows or particles smaller than 3 micrometer. It may seem that the maximum energy point is located at the geometrical center of this focus transducer. However, that's not actually the case. This is because the piezoelectric substrate on which the electrodes are deposited is anisotropic. The material we commonly use, lithium niobate or Alen, is crystallographically anisotropic. So when we cut an Alen ingot into thin wafers, the source velocity changes depending on the cut direction. As a result, due to this anisotropy, waves propagating in different directions travels at different speeds. And because of that, the actual focal point where the wave amplitude reaches its maximum is not at the geometrical center, but at a slightly shifted position. So in my work, I aim to analyze how key design parameters of focus transducers affect energy focus behavior, and to identify where the actual focal point appears depending on these 4 design parameters. First, I conducted a parametric study through numerical analysis. This figure shows the calculated wave field generated by a focus transducer. I investigated how the number of electrodes and the angle of focus transducer affect the focal point position, and found that these 2 parameters do not significantly affect the focal point position. Next, I performed numerical investigations by varying the curvature radius and acoustic wavelengths. The results are summarized in the graph on the right. As you can see, the amount of actual focal point shift is proportional to the curvature radius and inversely proportional to the wavelength. So I divide the curvature radius on the horizontal axis by the wavelength, and then the multiple lines merged into a single curve. Based on this result, I assume that the actual focal point position is affected by these 2 design parameters. Next, I conducted an experimental analysis using acoustic stream flow. To minimize the wave attenuation within the PDMS microchannel, I made a microfluidic chip by attaching a PDMS membrane within the acoustic window under the microchannel. Then, I analyzed how the velocity of the focus flow-induced acoustic stream flow changes by varying the distance between the focus transducer and the microfluidic chip. I assumed that the flow velocity would be the highest at the actual focal point. Here are the experimental results. The small mark shown here indicates the geometrical focal point. I observed that the acoustic stream flow became faster when the microchannel was located beyond the geometrical focal point. And this graph shows the velocity change depending on the microchannel position when the wavelength is 20 micrometer. And I plot the experimental results in the same format as the numerical result. However, the trend was different from the numerical prediction. A smaller curvature radius resulted in the actual focal point position farther away from the transducer relative to its size. I also tried to visualize it using PDMS. In this case, this microchannel was empty and this gap is PDMS. We observed an optical contrast in the PDMS, which was caused by reflective index variations induced by pressure changes from the acoustic wave. One interesting thing is that the actual focal point with maximum intensity matched the result observed from the acoustic stream flow analysis. when the curvature radius was 1 millimeter and the wavelength was 40 micrometer. The actual focal point was experimentally found at a position about 2.5 times the curvature radius. And to verify this result for the future work, I plan to directly visualize the wave field using a high-frequency laser Doppler bimodalometer. That's all for my presentation. If you have any questions, please feel free to reach out me. Thank you for listening.